Then the group 5 is called, that is the nitrogen group. That nitrogen, that is NPAXSBPI. That is nitrogen group. They are called the nicogens. That's what we call them, nicogens. Then group C. Now, in this course, periodic table, what I'm going to be doing, I'll be showing you guys just slides. Although I will not be reading everything, I'll just pick some from the slide, then explain, then go to the other slide, then just pick some and explain. Just like I'm just explaining your textbook or your note to you. Then this is the material I'll be using for now. Got this from a place, Wikipedia. Then now, the periodic table, also known as the periodic table of the chemical element, is a row and column arrangement of chemical elements. It is widely used in chemistry, physics, and other science, and is generally seen as the icon of chemistry. Now, periodic table is the arrangement of elements in order of increasing atomic number. Take note of that. It arrange the elements in order of increasing atomic number. Now, there are some properties of this periodic table that you ought to something like there are something like ways in which this periodic table is actually arranged. Let me show you some of the ways. All right, this is the periodic table we are actually talking about. I hope you know the meaning of horizontal. When I say the thing is in horizontal row and vertical column, I hope you know the meaning of that. So let me even show you what we mean. This 1 to, I don't know if you can see it, this 1 to 18, that number 1 is vertical column, that number 2 is another vertical column, number 3 is another vertical column, number 4 is another vertical column, to number 18. Then the other one that shows the period is from number 1 to 7. It's in horizontal row. It's in horizontal direction. Horizontal direction. So if you have this, okay, let me view it so that you see it very well. So that you see it very well. So do you see it? This one shows the group. That's 1, 2, 3, 4. We'll use this one. If you check this one now, we have the S block elements. Okay, let me just first explain the group. We have group 1A, group 2A. You can see them. Group 1A is hydrogen, lithium, sodium. Okay, that all those yellow group, check those dark, not the light yellow, the dark yellow. That's H, lithium, sodium, potassium, rubidium, cesium, and francium. You can see them there. Then group 2A. You see that group 2A. So all those A are the ones we do call. So you check this because I like this periodic table very well. This one now because it's showing almost everything. Now check this group. The first thing I want you to check for me here is I already show you the meaning of this one. Is this number 1 to 7 means period. This period 1, hydrogen, helium, period 2, heat, lithium, beryllium, and the other one, and so on. That is period 1 to 7. Then this group 1A, that is 2A. We have group 1A. This 1 you are seeing there is Roman figure 1 and 1. This 2 and Roman figure 2. Okay. Then you move to group 3B, 4B, 5B, 6B, 7B, 9, 8B, and 1B, then 2B. You can see it there. So those ones are not much problem. From this 3B to this, from this 1B, from this 11 and 12, 11 is 1B, 12 is 2B. Now from this 3B to this 12 are called transition metals. That's what we call them. They are called transition metals. Although we have some other section, like this number 57 and 89. You can see that's why they are using other colors to write them, because they don't belong to the transition metals. So you can see this one where they belong to. Check this color, because this color differentiate them. This color differentiate them. So we can also check their color trend. We have the Latinite series and the Artinite series, rare earth elements. Rare earth elements. They are the Latinite and the Artinite. You can see them here. You can see them here. Although they are not D block, they are F block elements. we call them F block elements. Call them F block elements. So this part of transition metals now that went to join this part of earth, real earth element, that is 71, that is 57, and what's it called, 89 are part of this lightinite and actinite. That's why they use other colors to write them. So these colors are just to tell you the particular element in this group. So group 1 now, they are called alkaline metals. That's what we call them. I'll also show you that very soon. I'll show you so that you see them. I'll show you so that you see them. Then you can see others here. You can see others. You also have others here. So let's first of all look at this group 3A. Forget about that. Group 13 is also called group 3A. Take note of that. Group 13 is called group 3A. That's what we call them. Then group 14 is called group 4A. Group 15 is called group 5A. Group 16 is called group 6A. Group 17 is called group 7A. Then group 18 is called group 8A. Now, this group 3A, 4A, 5A, 6A, 7A, and 8A, we call them group 3, group 4, group 5, group 6, group 7, group 8. So group 13 is also known as group 3. Group 14 is also known as group 4. Group 15 is also known as group 5. Group 16 is also known as group 6. Group 17 is also known as group 7. Then group 18 is also known as what? Group 8. Now, from this group 3A to group 8, that is group 3 to group 8, they are called the p block elements. That means they have their p orbitals being filled. This one have p orbitals being filled. Then from this group 3A to group 3B to group 1B, they are called d block elements because they have their d orbitals being filled up. All those ones are called transition metals. So the d block elements are also called the transition elements or transition metals. Then this other one, which is the actinite and the lightinite, they are not even part of the periodic table. They added them to somewhere in the downside. It's like you are not part of us, go and stay in this place. They are called the F block elements. They have their F orbitals being filled up, so they are called F block elements. Then the S block elements are group 1 and 2. The one called S block element are the group 1 and the group 2. So please take note of these blocks. You see F block, D block, and so I already gotten that. Then if you check, we can just want to get elements that are in the same group. Now, if you know elements in the same group, for example, now there are some things you should take note of. This group 1A, 2A to 3A, 4A, I will jump this transition element. If you want to call it now for me, just call group 1, 2, then jump this transition element. Jump these transition metals. Go and start from this next one. That group 13, that will be group 3, group 4, group 5, so that it will end at this group 8. End at that group 8. Although this helium is still S block. Take note. Helium is still S block element. It's not P block. Take note of that. That is a section of this periodic table. Nobody is 100% perfect, so we still have to manage it. It's very, very important. So all this group 1, group 2, group 3, I have already told you. All this 3B, all this B part, just throw them away. Forget about those one first. All of them, they are called, all this from this 3, the B elements are called transition metals. The A group, like group 1A, 2A, 3A, 4A, 5A, 6A, 7, 8A, 8A are the main group. So take note of that. Alright, take note of this. There's also called valency. And the oxidation state. Now, valency is the combining power of an element. And valency is also something like valence electrons are those electrons that an atom can either something like lose or gain or even share when you are doing chemical bonding in bondings. So we can use this group 1, group 2, group 3 that are just this A part 2, not B part. You can use it to get the number of valence electron in the atomose share of an element. For example, now group 1 will have one valence electron in the atomose share. The group 2 will have 2 valence electron in the atomose share. Then this group 13, which is group 3, will have 3. Group 4 will have 4. Then group 5 will have 5. Group 6 will have 6. Group 7 will have 6 electrons in the atomose share. Then group 7 will have 7 electrons in the atomose share. Then group 8 will have 8 electrons, which is now completely filled up in the atomose share. Now, this one that has group 7 now, which is group 17, that have 7 electrons in the atomose share, it will be very easy. It will be easier to gain 1 more than to lose 7. So that is why in the something like ionic state of all these halogens, which is the group 7 elements, they will rather gain 1 to be completely filled up than to lose 7. So that's how the thing is. For example, now group 6, which is the oxygen group, we either gain 2 to become 8 than to lose 6. Group 5 we either gain 3 than to lose 5. So that's how the thing is. Then this group 13, group 4 is just having, it's either it gain 4 or loses 4 to become stable or to form the octet or duplex state when you are doing electronic configuration. Now you should know how to do electronic configuration using the something like a Boyce model, all those share model and half-valve principle and the rest. You know how to do electronic configuration. We have done that before. Now, let's give them names. Let's give them names. I already told you from all this B part, from all these 12, from 3 to all these 3, 4, 5, 6 to 12, they are called transition metals. I'm not including that. I'm just doing about 1 to 13, 18 to 18. About 1 to 30 to 18. Now, this group 1 are called the alkaline metals. I don't know if you have heard about alkaline before, which is a basic oxide, and that is a basic oxide that are soluble in waters. All those bases that are soluble in waters are called soluble bases are called alkalines. That's what we call them. So they are formed from this exception from that hydrogen. Hydrogen is not even a metal. I don't even know what he's doing there. It's just that the guy is just complex. So try and know the isotopes of hydrogen. It's still very, very important. So that's why you see they don't even attach the hydrogen to this what's it called, they separated it from this lithium, sodium, potassium and the rest, because the guy is not even a metal, it's a non-metal. So I don't even know what it is, although he's still in group 1 because he has one electron in the atomose share. That's how the thing is. So from lithium, sodium, potassium and the rest, they will form alkaline, where they are something like forming like sodium hydroxide, where they are mixing with lithium hydroxide, potassium hydroxide, those are, and the rest. So group 1 are called the alkaline metals. This group 2, this one that is green, they are called the alkaline earth metals. The alkaline earth metals. Then the group, let's look group 14, which is group 4. This carbon group, they are called tetraes. That's what we call them, tetraes. Although some people call them metalliod. People call them metalliod. So metalliod is not actually that straight. I'll show you another stuff that will be showing the metalliods out. It's not actually that straight group 4. Although some people will say the group 4 are metalliod or semi-metals that have both characteristics of a metal and that of non-metals. So then this group 13s, they do call them trines. That is group 3. Then the group 5 is called, that is the nitrogen group. That nitrogen, that is NPAXSBPI. That is nitrogen group. They are called the nicogens. That's what we call them, nicogens. Then group 6 are called the chalcogens. That is the oxygen group, OXSETEPO. They are called the chalcogens. Then group 7, which is the fluorine group, are called the halogens. That is FClBroOAT. They are called the halogens, fluorine, chlorine, bromine, iodine, and so on. Then the group 18, which is the group 8, are called the noble gases or rare gases. So we have the group 1, alkaline metals, group 2, alkaline earth metals, then group 3, call them the trianes, then group 4, call them the tetranes or carbon group, or they also call them metalloids or semi-metals. Then group 5, the nicogens, group 6, that is group 16, the chalcogens, group 17, the halogens, group 18, the noble gases. Remember I told you group 13, also known as group 3, group 14 also known as group 4, group 15 also known as group 5, group 16 also known as group 6, group 17 also known as group 7, group 18 also known as group 8As. They are A's. Then the other traditional metals are the B part of it. So if you move from top to bottom, you know how to move from top to bottom now. That is, you are going from the top to the bottom. Things are going to be changing the periodic table. Things are going to be moving from more, maybe things will be more metallic. So we're going to look at some trends in the periodic table now. What is the meaning of atomic radius? What is the meaning of ionization energy? What is the meaning of electropositivity, electronegativity? We move from left to right and right to left, and we move from top to bottom or from bottom to the top. What is going to happen to the periodic table? So let's look at some trends in the periodic table. All right, the first trend we are going to look at now in this place is the atomic radius. The atomic radius is generally stated as the total distance from an atom's nucleus to the atom's orbital of electrons. A similar technique can be defined as something similar to the radius of a cycle, where the center of the cycle is the nucleus and the outer edge of the cycle is the atomic orbital of electron. So as you begin to move across or down the periodic trends emerge and helps explain how atomic radii behaves. At atomic radii, the size of atoms are dependent on the size of the outermost orbitals. Remember we said the distance between the nucleus to the outermost orbital. The outermost orbital, that is like you have the radius of a circle. It's the distance between the center of a circle to the circumference. That's just what we are trying to explain here. They generally decreases, They generally decrease going left to right along the main group element. That is group 1A to 8A. Because the nuclear charge increases, but the outer electron are still in the same share. All right. However, going down a column, the radar generally increases because the outermost electron are in higher share than that. A higher share that are thus further away from the nucleus. Now, when you are going down when you are going down a column, meaning of column, that you move from top to bottom in the periodic table, the atomic radius will increase. That means you move from bottom to the top, the atomic radius will decrease. Then, if you move from left to right, that is, you move from left to right, the atomic radius will do what? Will decrease. Take note of those two things. They are very, very important. Okay, let me show you something. Now, check this shares you are seeing, or these spheres you are seeing. If you move from top to the downside, that is from top to bottom, from the top side to the downside, it's called that each column will be increasing. Check from this lithium, that's Lina. Okay, let me show you something so that you see it very well. Then if you check everything, then you have to move from left to right, the thing will be decreasing in size. If you move from right to left, it will be increasing in size. From top to bottom, it will also be increasing. Then from bottom to top, it will be increasing. Also check for this. You can see it. So this explains everything. So this is all about atomic radius. You can see it yourself. Now the second trend is the one called ionization energy. The ionization energy. Now the first ionization energy of an atom is the energy required to remove an electron from it. So ionization energy can be said to be the energy required to remove an electron from a neutral atom. So they ask you, what is the energy required to remove an electron from an atom or from neutral atom? The energy is called ionization energy. That is what we call it. We do call it ionization what? Energy. Now let's check the trend of this energy in the periodic table. Now, this varies with the atomic radius. Ionization energy increases left to right and down to up, because electrons that are closer to the nucleus are held more tightly and more difficult to remove. You see why the thing is like that? So take note of that. So this varies with the atomic radius as well, because when you are moving from the bottom of a periodic table to the top, it's called that the atomic radius will be reducing in size. That means the outermost electron will be more closer now to the nucleus, and it is more difficult to remove electrons that are more closer to the nucleus than those that are very far from that nucleus. You just try and check it. For example, let's say we have a magnet and you have some things, you discover that from all these even this thing in electrostatics, when the distance is reduced, the force will be very high. When the distance increases, the force will be very low. So when the force is low, it's very easy to remove something. When this force is very high, it will be very hard to remove it. So electrons that are closer to the nucleus are more difficult to remove than those that are very far from the nucleus. That's why when you move from the down to the top, the thing will increase. Then when you move from left to right as well, we have more electrons to remove. So the thing will also, the ionization energy will also increases. So decrease will be in the vice versa. For example, if you move from top to bottom, the thing will decrease, ionization energy will decrease. When we move from right to left, it also decreases. It's just opposite to this one that is stated here, that energy increases from left to right and from down to top, or from the bottom to the top. So you take note of that, because electrons that are closer to the nucleus are held more tightly and more difficult to remove. So please take note of this. Let's look at other things. Next, electron affinity. Electron affinity. Now, the opposite property to ionization energy is the electron affinity. Take note, which is the energy released when adding an electron to the atom. Now, the energy released when an electron is added to a neutral atom is called electron affinity. That's what we call it. Electron what? Affinity. Now, a passing electron will be more readily attracted to an atom if it feels the pull of the nucleus more strongly, and especially if there is an available partially filled outer orbital that can accommodate it. Therefore, electron affinity tends to increase down to top. When you move from the bottom to the top, electron affinity will increase, and electron affinity will also increase when you move from what? From left to right. Take note of that. So if you are moving from the down to, if you are moving upward, if you are moving up, that is mean of down to top. Down to top means you are moving from the bottom to the upper side. You are moving upward. Electron affinity will, in the periodic table, electron affinity will be increasing. If you're moving from left to right, it will also be increasing. But if you move from right to left, it will decrease. If you move from top to down, it will also decrease. So you just take note of all these things. They are very, very important. Then the section we have in the periodic table are the noble gases. Since they are already filled up, noble gas is already filled up in the atomos share. So there's no need to be adding electron to something that's already filled up. So this gives the halogens in the next last column the highest electron affinity. So halogens has the highest electron affinity. So the periodic trend I want you to know now in this ionization energy, electron affinity, atomic radius is what happened when you move from left to right, top to bottom, and so on, whether they are increasing or decreasing. Very, very important. So let's look at the next one, electronegativity. Electronegativity. Now, electronegativity is just something like an ability for for an atom to attract electron to itself. Now, another important property of elements is their electronegativity. Atoms can form covalent bonds to each other by sharing electrons in pairs, creating an overlap of valence orbital. The degree to which each atom attracts the shared electron pair depends on the atom's electronegativity. That's what I'll try to explain. The ability of an atom to attract electron to itself. Now, electronegativity is the tendency of an atom towards gaining or losing electrons. Now, the more electronegative atom will tend to attract. Okay, now the more electronegativity is telling us how far an atom can attract electron or lose those electrons. So they are trying to tell you now that the more electronegative we tend to attract electron pair more, and the less electronegative we tend to attract electron less. Take note of that. It's very, very important. So more electronegative elements we attract electrons more. Then less electronegative elements we attract electrons less. Now, all those less electronegative elements are called more electropositive elements. You can see them. So when an atom is less electronegative, it will be more electropositive. So there's another thing opposite to what we are defining now called electropositivity. We'll also look at that later. So electronegativity is the ability of an atom to attract electron to itself. Now, the electron can be thought of as having been passed completely from the more electropositive atom to more electronegative one, though this is that is all. Now, electronegativity depends on how strongly the nucleus can attract an electron pair, and so it exhibits a similar variation to the other properties already discussed. So already discussed some of that. Electronegativity tend to fall going up to down. Now that means if you move from top to bottom in the periodic table, electronegativity will fall or it will decrease. It decreases. So, for example, now, let's say that is the highest electronegative elements. That is the most electronegative elements that we already discussed from electron affinity. We said the highest electron affinity, the ones that can something like attract the more electronegative elements are the one in group 7, which is the last one before you get to group 8, because group 8 cannot even do anything. They are already filled up. So if you move in that group 7, now group 7 are that is the highest electronegative element at the group 7. Okay, they will even discuss it later, although I don't have time to be reading. I told you before that I will not be reading all this stuff. So there's no time to be reading. So I'll just discuss it here. Let me just discuss what they are trying to explain here. Now, if you move from left to right, electronegativity, okay, where are we? We are in, when you move from the top to the downside, the electronegativity will fall. Like if you move from top to bottom, it will decrease. Then if you move from left to right, the thing will increase. Unlike the one we have been discussing, see they say we move from top to bottom, the thing will if we move from bottom to top. Now, if you move from bottom to top, electronegativity will increase. If you move from top to bottom, electronegativity will decrease. From the upper side to the downward side in the periodic table, down the group. If you move down the groups, the electronegativity will decrease. If you move from the downside of a group to the top side of that group, electronegativity will what? Will increase. Now, what about when you move from left to right? The thing will also increase. If you move from right to left, it will what? Decrease. Now, I told you the most electronegative elements we have are the halogens. So they are already something like listing it as the alkaline. The alkaline and alkaline earth metals are among the most electropositive elements. That is, the first two groups are most electropositive, while the chalcogens, halogens, and the noble gases are among the most electronegative ones. Now, electronegative is generally measured on the Pauling scale. On which the most electronegative reactive atom is fluorine, is given electronegativity 4.0, and the least electronegative atom is cesium, which is given 0.79. Now let me just give you guys how they were able to get this most and least. Look at it. Now, I told you guys that the most electronegative elements are those in group 7. It's supposed to be group 8, but group 8 cannot something like attract electrons again, because group 8 is already filled up. So group 7 now is now next to group 8. So group 7 is the most electronegative elements, which are the halogens. Now, if you move from the top side of that group 7 to the downside, the thing will decrease. If you move from the downside to the top side, the thing will increase. That means the first one in the group 7 will be the most electronegative element in the periodic table. That's why they said fluorine is the most electronegative element, because fluorine is the first element in group 7. Now, the least electronegative elements in the periodic table are those in group 1. Because when you move from left to right, the thing will increase. So if you move from right to left, it will decrease. So group 1 is the least. Then group 2, second to the least. Group 3, third to the least. Until you get to group 7, which is the highest. So in that group 1, among the least, we still have the least of the least. That is it. Although 6-zion is the second to the last in group 1. The second to the last in group 1. Group 1 elements are the least electronegative element in the periodic table. So the last in the group 1 from this trend, since we move from the top to the bottom, the thing will decrease. The last in the group 1 supposed to be the least electronegative element, but because of some minor or irregularities we do find in periodic table, then cesium, which is second to the last, is now the least negative element in the periodic table, and it should be the most electropositive element as well. So take note of that. It's very, very important. So now let's look at electropositivity. Now, electropositivity can be defined as the tendency of an atom to donate, not attract, this time around. Electronegativity is attract, while electronegativity is to donate electron to form positively charged cations. The property to form positively charged cation is mostly probably exhibited by the metallic element. So the only electronegative elements in this periodic table are the metallic elements. They are the only ones that can donate. Others can only attract. So why the only electropositive elements are the metallic elements, while the electronegative elements are the non-metallic elements. So non-metals are electronegative, while metals are electropositive. So take note of that. It's very, very important. But when you are asking you which one is the least electronegative element, is the one that is the most electropositive element is the least electronegative element, while the most electronegative element is the least electropositive element. It's as simple as that. It's just like logic. So that's how the thing is. So electropositivity is just the opposite of electronegativity, which I've already discussed. So we already said that in the group 1 element, the last one supposed to be the most positive element. But because of some irregularities that may occur, then cesium, which is the second to the last, happens to be the most electropositive element. So the last element in group 1 is supposed to be the most electropositive element, while the first element in group 7 supposed to be the most electronegative element. So fluorine is the most electronegative element, while cesium, which is second to the last in group 1, is the most electropositive element. Remember, when you move from top to bottom, something will happen in the periodic table to all these atomic, all these trends, periodic trend like electroaffinity, atomic radius, electronegativity, electropositivity, and ionization energy. So take note of what will happen when we move from top to down and left to right. Now, from this now, when you move from, due to this explanation self, you can just discover that when you move from left to right, electropositivity will what? Will decrease. We move from right to left, electropositivity will increase because group 1 has the highest electropositivity element. So we move from group 7 to group 1, the thing will be increasing in electropositivity. Group 8 to group 1 will move increasing electropositivity. Then group 1 to group 8 will be decreasing in electropositivity. Then we move from top to bottom, electropositivity will increase. From bottom to top, the thing will decrease. That's why fluorine is the least electropositive element in the periodic table. I repeat, when we move from left to right, electropositivity will reduce or decrease. When we move from top to bottom, electropositivity will increase. So please ensure you know this periodic trend. They are very, very important. Now, I want to round up this class because it's already getting too long. I want to look at group 1 to group 8 elements. You can also read on them: group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8. Remember, group 1B to group 8B are the transition elements. And also remember the inner transition elements, which are the Latinites and the what? Actinites. Remember, group 1 and 2 with helium are the S block element. Then group 3A to group 8A are the P block, while group 1B to group 8B are the D block, which are the transition metals. Then the other inner transition something like the, what do you call it, the actinides and the latinides are the F block elements. So also know their block. If they ask you what are the S block, what are the D block elements, so that you know how to code them. They are just getting from those that have S orbital, filled up, D orbital, P orbitals, and these others. So let's quickly look at this group 1, which are the alkaline metals. Although group 1, 2, 3 are metals, group 4 are semi-metals or metalloid. That's what they call it. Then group 5 to 8 are non-metals. So that's how the thing is. So we group them into metals, non-metals, and metal, semi-metals. So metals, you can go and read on metals and their compound, semi-metals and their compound, and the non-metals and their compound. So I'm just going to take a look at group 1, group 2, group 3, group 4, group 5, a little. So let's look at group 1, which are the alkaline metals. So group 1 are called alkaline metals, which consist of chemical elements lithium, sodium, potassium, rubidium, cesium, and francium, together with hydrogen. The reason why hydrogen was not listed with them before at first was because hydrogen is not an alkaline metal. Hydrogen has just similar property of a metal, but it's not a metal itself, it's a non-metal. Although it has properties of a metal, like have positively charged ion, in its ionic state, does that of a metal, which are all these electropositive behavior. It has it, but it looks like a non-metal in nature, but it behaves somehow like a metal. So it's found in group 1, and it has a valency which is equal to 1. You can also check the electrons of this hydrogen. Now you can see the group 1 elements, just do them and their names, which are the alkaline metal. Let's look at, and they are called lithium family. Look at group 2, because I just go to look at them and identify them little by little. Now the group 2 are called the alkaline earth metals. You can see them. They have the beryllium, magnesium, calcium, strontium, boron, radium. They have very similar property. They are all shiny. I love that one. Silvery, white, somewhat, and so on. I love that one so well. Let's look at the other one, please. The boron group, which is the group 13, which is group 3A. Group 13 is seen as group 3A. Group 3A as listed as follows. The first one is boron. Although boron, they do call it metalloid. It's part of metalloid. Then we have the aluminium. We have the gallium. We have the indium, thallium, nihonium. The elements in the boron group are characterized by having 3 valence electrons. In the hydrogen group is 1 valence electron, group 1 valence electron, group 2 valence electron. Then this group 3 now is 3 valence electron. The element have also been referred to as the trias. The trias. Take note of that. Very, very important. Now the next one, which is group 4, also called group 14, is the carbon group, which some people do call semi-metals or metalloid, although it's not actually that straightforward. Because metalloids move from boron to silicon, then they now move. It's not a straight line in the periodic table. So this carbon group, which is group 4, is comprised of carbon, silicon, germanium, tin, lead, and so on. So let's look at the next one. Now the group 5, which is also the group 15 elements, are called the nitrogen groups, which are having a trivial name called nicogens. The nicogens. Now the nicogens are having the following elements, which are the nitrogen, phosphorus, arsenic, antimony, bismuth, and so on. So please take note of them. This one is the group 5 element. They are called the nicogens, nitrogen group. Now the group 6 elements, which are the oxygen group. The group 6 elements, which is the oxygen group, are called the chalcogens. That's what we call them, the chalcogens. You can see them. We have oxygen, sulfur, selenium, tellurium, and the radioactive element polonium and livermorium. You can see them. These are the chalcogens, which are the group 6 element or 16. Call it either 16. I call it the group 6A. And these are the group 7 elements. This is the group 17. The one they call group 17, and they are called the halogens. They are the halogens like fluorine, chlorine, bromine, iodine, and the astatine. And they are all non-metals and having 7 valence electron in their electron share. The meaning of the word halogen: the word halogen means salt forming compounds. Take note of that, and so on. So group 8, which is the group 18, are called okay, let me just look at that. Alright, the group 18 elements, which are the group 8 elements, 8A's, are called the noble gases or the inert or rare gases. Now, the noble gases or the inert gases, which means that these elements are chemically inert and do not take part in any reaction. That's why we do call them inert gases or noble gases. They are comprised of the helium, neon, argon, krypton, and xenon. So you can take note of their chemical formulas and the rest. I love these stuff very well. Especially these noble gases. I love them. And you can see the light they do give if they are used in lamps. You can see the reflection they do give they are using lamp. They are very lovely. He, neon, that is helium, neon, argon, krypton, xenon. You can research more of this. Just research on can see the colors in when it's not like they are glowing. Yeah. So the only liquid metals are solid, but the only liquid metal we know at room temperature is the one they call mercury. That is the only liquid metal at the room temperature. Now, history of the periodic table. The periodic table that is studied today is the modern periodic table and was invented by Dmitri Mendeleev. However, Mendeleev was not the first one who grouped and arranged the elements in the form of periodic table. The following are a few attempts to classify elements that took place prior to the reproduction of the modern periodic table. Now, the first person that we are looking at here is the Artyom Lavoisier. In 1789, that is very far, Artyom Lavoisier was the first to classify elements based on their properties. He grouped the elements into gases, non-metals, and earthly elements. So you can see somebody first of all worked, he picked some elements, he grouped them. So these ones are called metals. These other ones are called non-metals. These ones are called earthly elements. So that's Lavoisier that did that. So take note of that. Then after several decades, in that is, if you check this year now, check this year, we have 1789. This one is 1829. So that's very far, more than 10 years. After several decades, John that is Johannes Debery now made an attempt to group elements based on similar in chemical properties. So another person also came to work on the same periodic table. He grouped elements into trade. That means this person derived the law of trade. So derived the law of what? Trades. He groups elements into trade. The middle elements atomic. Okay, the middle elements atomic weight in their trade stands approximately as the average of the first and third element into weight. This can also help define the properties of the middle element, e.g. lithium and so on. So this scientist was the one that discovered the law of trades. Take note of that. That's what I just wanted to get here. Then you see I have another one here. Okay, the attempt to classify elements did not stop here. It was in 1865. That is few maybe years after that the English scientist, the English chemist John Alexander Newland arranged elements in order of their increasing atomic weight. There's no between atomic number and atomic weight. Okay, he discovered a theoretical arrangement. He showed that physical chemical property of the 8 elements is similar to their property in first. Now, one thing I want you to know is that this person discovered the law of octaves. The Newland is known as the law of what? Octave. So Newland discovered the law of octave. The other one discovered the law of trade. Then if the Artyom Lavoisier was the first person that classified elements based on their properties. Take note of that. It's very, very important. Now, it was only in 1869. Okay, we have already done that. We have already done this now. Okay, we stop in this law of trade. Okay, let's start. The attempt to classify elements did not stop here. We continue. I just want you guys to get little things, just little things about this history. It was only in 1869 that Mendeleev published his paper in the Journal of the Russia Chemical Society. Where blah, blah, blah. Okay, you can look at it and see. Mendeleev successfully arranged all 63 elements that were known now into tabular form, which contain 8 columns and 7 rows. Now remember, we said the modern periodic table contains 18 column and 7 rows. So you can take note of that. So this is similar to the modern periodic table. So this work that was done by Mendeleev was the one this modern periodic table was coined from. It also contains some gaps which were later fed after the discovery of the new element. That was another great work that was done by Mendeleev. He gave something like, he predicted some elements that will be found in the future to be filled into his periodic table. It is almost impossible to do something like that. He was working, he found some elements, he arranged them. They discovered that some were not something like there. It was like, okay, based on this my work, based on this periodic stuff I've seen, this periodic trend I've seen, I something like the guy something like foretells some elements that will be discovered in the future. So I will check if I will see some of the elements and I will tell you. It even something like predicted their something like maybe their density, which was nearly to the something like density that was found, and some of the properties of the elements that was found later, and the element was discovered later. So the guy did a very great work. That was okay. Then Mendeleev was successful in classifying the element and showing the periodic similarity in element. However, there were a few anomalies in the arrangement which were later cleared by the English physicist Henry Moseley. Now, Henry Moseley periodic law. Now, this Henry Moseley was the one that something like arranged, like it's something like he rearranged, he worked on the periodic table that was done by this Mendel. Although so many other scientists worked on the periodic table, it was some scientist that discovered the elements that Mendeleev foretell that they will go to something like be found, discovered. It was some scientist that did that. They are not here now. So Henry Moseley showed that the chemical and physical property of elements determined by the atomic number is determined by the atomic number, not by the atomic mass. Now, somebody, that's why the periodic table was even arranged in order of increasing atomic number. So he restated the periodic law as physical and chemical property of element are a periodic function of its atomic number. That is the periodic law, that the physical and chemical property of an element are a what? Periodic function of what? The atomic number, not the atomic mass. Take note of that. Okay, Moseley periodic law is also known as the modern periodic law, and it paved the way to the modern periodic table. So Moseley was the one that works on the Mendeleev's work to bring out this modern periodic table. All right, now let's get the elements and symbols. Yeah, all the elements we have in the modern periodic table and their symbols. Now there are some that follows their name, while others don't. For example, on this hydrogen, you can see the atomic numbers: number 1, number 2, number 3, number 4, number 4, 5, 6, and so on to 118. So you have hydrogen, helium. Hydrogen is H, helium He, lithium, beryllium, boron, we have boron. You can see the symbol for boron, B, symbol for carbon, nitrogen, oxygen, fluorinium. Then check the symbol for sodium, Na. Taking note of that. Magnesium, aluminium, phosphorus, silicon, sulfur, chlorine, argon. Check the symbol for potassium, K. Take note of that. Check the symbol for that potassium is K. Then we have calcium, we have scandium, we have titanium, we have vanadium, we have chromium, we have manganese, we have iron, cobalt, nickel, copper. Check the symbol for that copper. It's not Co, it's Cu. Then we have zinc. Then also check the symbol for this iron. Check the symbol for this iron. Iron is not IR, it's Fe. That is symbol for iron. Take note of that. It's very, very important. Still important. We have gallium, germanium, arsenic. Then we have the next one, selenium. We have bromine. We have krypton, rubidium. We have strontium. Now check the symbol for that strontium. Sr is not St. Even rubidium is Rb. You can see the next one, number 39. You can see we have number 40 and a symbol. Californium, we have niobium, number 41, number 42, number 43. You can see their symbols on their name. You can see rhodium, number 45. You can see palladium. You can see it. Silver. Now check the symbol for that silver. Ag, not Si. You can see that. Cadmium. You can see that symbol. I will not be calling their names again because of time. So you just be looking at the names. I'll just be calling their number. Look at that number 49. Indium. You can see it. 50. You can see the tin is SN, not TI. You can see the symbol for that tin. I will see the symbol for that. This antimony. Check the symbol for that antimony. It's SB. No, there's no even S in the spelling self. So take note of all those ones in which the name and their symbols don't even something like correspond at all. Take note of those ones very well. So we have iodine. You can see iodine there. Xenium. You can say cesium. Have barium, not baron. Barium. Have lanthanum. Lanthanum. See that? You can see there's many of them here. See their name. Their name. You can see the name. So you can see. I'm just looking for. There's one I'm looking for now. If I just see anyone, I just this tungsten. Take note of that tungsten. Number 74. Tungsten. W. That is the symbol. Take note of that. Take note of that one. Then look at this gold. Number 79. Gold. AU. That is the symbol. Look at mercury. HG. That is the symbol. Thallium. So those one, that one still follow a little. I have lead. Look at this lead. PB. That is the symbol. We have bismuth. Bismuth. Then although you are supposed to study all these elements one after the other. That is meaning of periodic table. You study all the elements. Although because of the nature of the periodic table, in the sense that some particular element that belong to the same group will have a similar chemical property and so on. You may not even need to study everything. You just study them in groups. That's why elements they were presented to you guys in periodic table in groups. Periodic table is not to give you problem. Periodic table is to simplify the element for you so that you will see them. So that you will see them. You can even see Californium, although those one follows. So most of these elements from all these it is something and being at something to 118 where something like synthesized. Most of them are not natural in the lab. You can see the number 118.